Welcome, this is Dr. Plague, and this is part 3 of developing a clock source for future homemade CPUs. In part 2, I had my design complete except for the 555 timer circuit. I can single step the clock, and I can use the run stop switch to send through a fixed frequency running clock source. So now what I want to do is to create a 555 timer circuit that will allow me to adjust the frequency from around 1 Hz up to about 10 kHz. But the trick here is that I want to use a fairly low valued potentiometer, one that's only 10k ohms. This may not sound too difficult, but I will show why this could be challenging. Now, before we continue on, one thing I'd like to mention about the 555 timer is that there will be a lot of current sloshing around when we charge and discharge the timing capacitor. This could disrupt our power supply, especially since I've built this thing on a breadboard. There can be a significant amount of resistance on this breadboard, which can create a voltage drop when we're sloshing current around. And if we look at the 555 datasheet, we can see that they recommend a 0.1 microfarad capacitor on the power pins. So I'll just add a 0.1 mic bypass capacitor on the 555 power pins, pins 8 and 1. Pin 8 is VCC and pin 1 is ground. I probably should have added this in the last video, but you know what they say, better late than never. It also wouldn't be a bad idea to add some additional capacitors to the power pins of each IC, but I'll just place one at the timer IC for now. Let's now take a look back at the schematic to the original fixed frequency 555 timer circuit that I breadboarded up in the last video, with the added 0.1 mic bypass cap. Now, I don't care what the duty cycle of this timer is, because I'm going to send it through a frequency divider anyway. It'll be divided by 2, which will create nearly a 50% duty cycle in the end, regardless of the starting duty cycle. With that in mind, let's talk about how we could create an adjustable frequency using a potentiometer with this 555 timer circuit. There are several ways we could do this, and there are some interesting designs we could come up with, but I'm going to try to keep it simple. And one way we might consider is to use the control pin on the 555. Normally, we would just decouple it to ground with a 10 nanofarad capacitor. But let's take a look at the simplified 555 schematic in the datasheet to see what this pin does. Now, we can see there are 3 supposedly identical resistors here creating a voltage divider such that this upper comparator sees 2/3 of VCC and this lower comparator sees 1/3 of VCC. This means that the timing capacitor will continue to charge and discharge between 2/3 VCC and 1/3 VCC. And we can also see that the control pin goes to this junction between these 2 resistors, so we can control these voltages. Whatever voltage we place on the control pin should set the upper voltage that the timing capacitor will charge up to. And since we have 2 identical resistors from the control pin to ground, we will see half the control voltage at the lower comparator. So the timing capacitor should charge and discharge between the control voltage and half that voltage. Now, let's say that the ground is here, and we apply a positive voltage of this magnitude to the control pin. So now the capacitor should continually charge and discharge between this voltage and half of that. Let's say we lower the control voltage. Now the capacitor only needs to charge between here and here. Since the capacitor doesn't need to charge or discharge as much, we would expect it to oscillate faster and give us a higher frequency output. So we would expect a lower frequency with more voltage on the control pin, and a higher frequency with less voltage on the control pin. This seems to make sense, doesn't it? What we could do is place the potentiometer from VCC to ground, then connect the wiper to the control pin like this. Now, as we adjust the potentiometer, we change the voltage to the control pin. Let's quickly try this out. I'll just put this little potentiometer right here. Then connect this side to VCC and this side to ground. Next, I'll connect the center pin, which is the wiper, to the control pin. Great. Let's apply power and see what happens. Let's put it into run mode. And we can see the LED flashing. If I adjust the potentiometer by rotating it counterclockwise, the flashing does appear to slow down. So far, so good. What happens if I turn the potentiometer the other way? The frequency does speed up. But, whoa, what happened there? If I turn the potentiometer to the extreme, we can see the flashing actually starts to slow down. What in the world is causing this? Well, let's connect up a scope. First, I'll connect channel 1 up to the control voltage so we can verify it actually varies from 0 volts up to VCC, which is 5 volts. The control voltage will be shown in yellow, and each division is 1 volt. And I turned on the 4th channel, which is disconnected so we can see where ground is on the screen. It just gives us a reference to look at. Yeah, this is a little finicky. This is not the best potentiometer, but as I turn it, it does indeed adjust the full range. Now, I want to look at the charging and discharging of the timing capacitor on channel 2. But before I connect that up, let's set up a math waveform on the scope. What we're looking at in red here is 1/2 of the voltage on the control pin. So now we would expect the timing capacitor to continually charge and discharge from the red line up to the yellow line. So now let's connect up channel 2, which will be in blue. There, that's looking pretty good. This is about what we would expect. Now, if I start adjusting the control voltage, everything looks good until we get up to about 4 volts. Then the capacitor voltage starts lagging a bit. I actually would expect this because the 555 is not a rail-to-rail device. And in reality, it's not changing our direction of decreasing frequency. It's just affecting the rate of decrease. Now, let's start lowering the voltage to see what happens when the frequency starts to decrease at the lower voltages. Everything looks good until we get to about 1.7 volts. The maximum charge on the cap does not seem to drop below 1.7 volts. But the lower end drops some more, so we are now increasing the charge range, effectively lowering the frequency. But why is this happening? Let's take a look at the 555 datasheet to see what we can find. So, the voltage on the control pin shows a maximum of VCC. It doesn't show a minimum. And the control voltage at VCC equal 5 volts shows between 2.6 and 4 volts. But that's for an open circuit, so that's not helping. It doesn't really state at what voltages the comparators are going to work at. If I were at work, usually in a situation like this where I need more info than I can find in the datasheet, I would contact an FAE from the parts manufacturer and question them about it. They can usually find the answer you need, even if they need to go talk to one of their engineers. But let's look at another manufacturer's datasheet. And while they show the same info as the last one, they do show us an interesting graph in Figure 13. There's a modulation input voltage going to the control pin, just like what we're doing. And look at this. When the control voltage lowers, we can see the same thing in their capacitor voltage. The change in frequency does seem to switch directions and start decreasing down here. The upper end of the charge seems to flatten out, just like we saw in my circuit. So it looks like this is to be expected. Now, one thing we could do is limit the voltage range on the control pin, maybe by adding a resistor between the potentiometer and ground, like a 6.8K. Now we can't get below 2 volts. So the frequency no longer starts to decrease at lower voltages. Keep in mind that if you're trying to build this circuit, you may not see the same results, depending on which flavor of 555 timer you use. But it looks like the NE versions act this way. Your mileage may vary, but in any case, I'm not seeing enough of a frequency variance to reliably use this method to get from the single hertz range up to around 20 kilohertz. So I'm going to abandon this method and look at alternatives. Another way to go about this is to add the potentiometer at either R1 or R2. This would change the time to charge and discharge the timing capacitor, effectively changing the frequency. The formula for the frequency is 1 all over the natural log of 2 times R1 plus 2R2 times C. So it might make sense to place the potentiometer at the R2 position so that it creates the largest variance of frequency, since we multiply R2 by 2 in this formula. But let's see what we would need to do to get the range of frequency that I'm looking for. Let's suppose that R1 is 0 ohms, which, by the way, we would never want to do because this creates a dead short between VCC and ground when the discharge pin is pulled low. But I'll just pretend it is 0 ohms to get the starting value for the capacitor. Now, to calculate the starting capacitor value, we could swap frequency and C in this formula. Okay, let's start plugging in some values, and I want to start from the lowest frequency. We have 2 times 10K, which is 20K, plus 0, times the natural log of 2, times 1 hertz, and all that is divided into 1. So that gives us a capacitor value of approximately 72.1 microfarads, which is fairly large for the highest frequency that I want. Since I want a high frequency of around 10 kilohertz, I actually want the 555 to oscillate at 20 kilohertz, since the clock circuit will divide that by 2. So now let's see how much resistance we would need to get up to 20 kilohertz. I can swap the resistances with the capacitor here for this formula. Okay, we have the 72.1 microfarads times 20 kilohertz times the natural log of 2, and we'll divide that into 1. So we would need R1 plus 2R2 to equal 1 ohm. That is not going to work. This would create a near dead short from VCC to ground during the discharge, and we can't have that. But wait, we actually don't need to get down to 1 hertz. We only need to get down to 2 hertz since we will be dividing that by 2. So let's recalculate this. 2 times 10K plus 0 times the natural log of 2 times 2 hertz divided into 1 gives us only 36.1 microfarads now. A little better, but let's finish the calculation. That times 20 kilohertz times the natural log of 2 divided into 1 now gives us 2 ohms. That's still almost a dead short, so this isn't going to work. So what can we do? Well, let's approach this from the other direction. We began calculating the component values starting with the lowest frequency. So now let's start with the highest frequency, which in my case will be 20 kilohertz. First of all, let's choose the lowest values of resistors that I want to use. Since we have 5 volts, I want to choose resistors no lower than maybe 200 ohms or so. While I do have 200 ohm resistors, perhaps 220 ohms are more common since the 200 ohms aren't seen in anything below the E24 series. So I'll start with 220 ohms. Now let's calculate the capacitor that we would need to get to around 20 kilohertz. We have 2 times 220, which is 440, plus 220, bringing us up to 660, times the natural log of 2, times 20 kilohertz, and after dividing that all into 1, we get about 0.109 microfarads. So I'll just choose a 0.1 mic cap. And let's calculate the frequency with these components. We have 2 times 220 plus 220 times 0.1 mic times the natural log of 2 divided into 1, which gives us about 21.9 kilohertz. Good enough. Now let's see how much the resistors would need to change to bring us down to 2 hertz. So we have 0.1 microfarads times 2 hertz times the natural log of 2 divided into 1, which gives us about 7.21 megohms. Wow! How are we going to do that with a 10K potentiometer? Well, let's think about this. What if, instead of using the potentiometer to directly limit the current to the capacitor, what if we use it to control some type of a valve which limits the current? We could use the potentiometer to completely open the valve or completely close it, giving us a very wide range of resistance to the capacitor. Sounds fantastic to me, but what do we use for our valve? Well, the word valve can be used as another term for a vacuum tube, but I don't really want to design a vacuum tube into my circuit, do I? That might be interesting, but what ended up replacing vacuum tubes? The transistor. Why not use a transistor to limit the capacitor current? Sounds fair to me, so let's try it. To simplify things, I'll just use a bipolar transistor since they're fairly commonly used on breadboards. So first I need to decide where to place the transistor. Should I place it in with R2 since that's where I would have placed the potentiometer? No, I'm not going to choose to place it there because the voltage is not stable. The capacitor charges and discharges, causing a shark fin type waveform there. I want to provide a stable voltage to the base of the transistor, and if the emitter and collector voltages are bouncing all over the place, then that might prove a little difficult. So, I want to place it at one of the rails, either VCC or ground. I'm not going to choose ground because that would put the transistor under the capacitor, and I want it above the capacitor, so I'll place it up here at VCC. Since I'm placing it up by VCC, I'll choose to use a PNP transistor, specifically a 2N3906, which I have plenty of. And I'll use the potentiometer to control the voltage to the base. And I'll just place a 1K resistor here to limit the current into the base. I'll also add in a 33K resistor down here between the potentiometer and ground to limit the voltage to the base. Now this looks good, but if we cut off too much current through the transistor, then we might stop the clock entirely, and I don't want it to go much under 1 Hz. So I'll add a resistor here to limit the lower end of the frequency range. I had previously calculated 7.21 megohms for a 2 Hz oscillation, so I'll just choose a 10 megohm resistor, which should give us just under 2 Hz, and when divided by 2, we'll get just under 1 Hz as the final output. Great, let's breadboard this up. Let's remove this old potentiometer circuit. Then I'll just add in the 220 ohm resistors and the 0.1 mic cap to verify that we get a frequency somewhere close to 20 kilohertz. I'll take out this 10K resistor and the 10 mic cap. And I'll just put a 0.1 mic in here. Then I'll add in a 220 ohm resistor in place of the 10K. Come on, get in there. Now, let's replace this 10K with a 220 ohm. And I'll just connect the scope probe to the output pin. And let's power this up. We're getting somewhere around 17 kilohertz, close enough for me. We can pull this in more later if needed. Okay, let's disconnect the scope and add in the transistor circuit. I'll just pull this 220 ohm out so I can connect it to the collector of the transistor. And let's put the transistor in right here. I'll connect the emitter to VCC. And I'll put the 1K base resistor in right here. Then I'll drop the potentiometer in such that the wiper connects to the 1K resistor. And I'll pull this end of the potentiometer to VCC. And connect the other end to ground through a 33K resistor. This circuit is a little sloppy, so I need to make sure not to short anything out. As I've said in the past, I'm not the neatest plague. I think the only thing I have left now is to add in the 10 meg resistor from the collector to VCC. There, let's connect up a couple scope probes. The first channel, which is yellow, to the output LED, which is where I'll be measuring the frequency, and the second or blue channel to the 555 output. And now let's power it up and test it. That's not looking very stable. It could be the cheap potentiometer. Let's make some adjustments to it. Let's take a look at the lower end of the frequency range. And we're getting just under 1 Hertz. Let's go somewhere in the middle. And this looks to be about 4 kilohertz. Just over 7 kilohertz. And we're getting over 10 kilohertz, but that's kind of bouncing around. Let's hit the transistor with some freeze spray. I'll bet we'll cause some havoc. Look at that! It did not like that at all. The transistor looks to be very sensitive to temperature. Well, that was not very stable, so what could we do to help stabilize it? How about we place R1 between VCC and the emitter of the transistor? What will that do? Well, that'll give us a more predictable emitter voltage and a more stable emitter current. And since very little of the current will travel through the base, the collector current will be almost the same as the emitter current. This will also give us more of a linear charge on the timing capacitor, which will help to increase the upper frequency. But we must also adjust the 33K resistor, since we now need more voltage across the emitter. So I'll just choose 10K. Cool, let's give this circuit a try. Let's swap this resistor with this wire over here. And then change out the 33K with a 10K. Okay, let's give this version a go. And if we run it, yeah, that's looking a little better. Now we get a much more stable frequency. And of course, it would help to have a better quality potentiometer, but this isn't bad. Let's test out the low end. And I'm getting about 3/4 of a hertz, which is a little under 1 hertz. Perfect. Let's bump it all the way up. And it looks to be about 11 kilohertz. Fantastic! I like this. Let's check the temperature stability and hit it with some free spray. No change. Absolutely beautiful. Yeah. Now, there's only one thing left to do, and that is to test it out with the Plague Mark I homemade CPU from my previous videos. So let's pull that in and connect this all up. Okay, here it goes. Single stepping is working. I'll turn on run mode. Let's change the frequency. Getting faster. Yeah, look at that. Let's move it up to an insane speed. And drop it back down. This all looks great. Works just the way I want it. Beautiful! This will be the circuit that I'll use in future videos. Not the greatest little contraption, but it does the job. And I was able to get an adjustable range from at least 1 hertz up to 10 kilohertz. And in fact, the range was a little greater than that, from around 3/4 of a hertz up to about 11 kilohertz. So I did hit my goal, and I'm very pleased with that. Now, there are other things I could do to it, such as add in the capability to choose between an adjustable frequency or a crystal oscillator, such as the 1 megahertz crystal oscillator I used in the last video, but I'll just keep it as is for now. If you make one of these, then you can do whatever you want with it, and design it to your own specs. And who knows, you may have some better ideas than mine, so go ahead and experiment. Well, that's my final video for designing a clock source. I may come back to it in the future, but for now I have no plans of doing that. My next videos will probably be on some design tips for homemade CPUs, then I'll get back to the CPUs and work on the Plague Mark II. That's it for this video. Thanks for watching, and I'll see you next time, right here on Dr. Plague.